Zaina Tarafder is right here. And she's going to talk to us about the clustering of new stars and nebulae. She understood that correctly. And she's doing her graduate work here. You graduate student?
Undergrad.
Okay. I'll let you.
Thanks.
Thank you. Hey.
The microphone does not work, so we kind of need here.
I know there's a mic in here that works. And
I'm getting it pulled up for you. Okay, you should be good to go. But you're gonna want to move this, yeah, so you can see your thing. And we can make this the cast so you can see yourself if you'd like. There we go. All right, we can change the camera.
love it.
All right. Hi, everyone. My name is Zaina. I'm a third-year undergrad at UVA. And today I'm going to be talking to you about the investigation of the clustering of massive stars in GH2 regions. That's a lot right now, but we're going to unpack it as we go. And my advisors for this project were Dr. Yichen Zhang and Jonathan Tan. I'm going to talk a little bit about the actual, okay, I'll just use this. Okay. How do I make this? Okay. So. Oh, okay. All right. So I'm going to talk a little bit about the Virginia Initiative of Cosmic Origins. This is the program that I was a part of last summer. It's a collab between Chalmers University and Gothenburg, Sweden, and UVA. Teddy was a part of it too, so he's in that picture right there. And then all the way on the left, that's Jonathan Tan. He's like the main research advisor of the whole branch. He's looking over a lot of projects with a lot of students. So I really appreciated the opportunity to be out in Sweden last summer. And VICO itself is focused on cosmic origins. So most of the projects in our group are more centered around galaxy evolution, stellar evolution, and the beginnings of our universe. So yeah, that's me in front of Chalmers. This is a little bit what we're going to be talking about today. And first, we're going to be talking about what massive stars are, how they form, and why it's important to study them in the first place. I included this quote by Carl Sagan. He's a famous astrophysicist, and he talks about how we are all made of stardust. And it's kind of just something that humbles me sometimes when I'm doing this sort of research, because we kind of come from the star formation process, and everything in our body is a result of that. And so why study stellar evolution? It drives the formation of all of our planets, galaxies, and is the foundation of all of the elements. And we're going to talk about star formation a little bit as well in a moment. And we are a direct result of that process. And studying stellar evolution can also help us understand and solve unknown astronomical phenomena like supermassive black holes, dark matter, dark energy, and exoplanets. So we're going to be talking about that as well. So how do stars form? I know we have different like levels of prior knowledge going on here. So we're going to start at the basis. So stars form from a molecular cloud, which is basically just a dense region, and you could find them in nebulas and H2 regions. We're going to be talking about that too. And due to the force of gravity and shock waves and all of that, it'll collapse over time, and then it'll basically have a very hot core. And that hot core rotates really fast, and then a very like all the material from the molecular cloud is going to start to rotate around it in a disk formation because of angular momentum. And so that disk is called our protoplanetary disk. And over time, as different elements move further away at different temperatures, elements behave differently. So the further out you go, we get more gaseous planets, and the further in you are, you get more rocky planets. So then we get a stellar system. with a young star, and this is for a main sequence star, kind of like our sun. So not all stars form this way. And then we have our stellar system surrounding it. And then kind of just to talk about how the star formation process is a cycle, we kind of go into this death process. It's a lot more, there's a lot more that can happen, but this is like a more simplified version of what could possibly happen when a star dies or when a main sequence star dies. But the research I'm actually doing now is more about the red giant planetary nebula transition. But you can get all of these outcomes like a white dwarf, a neutron star, or a black hole. And so we're going to be looking at high mass stars for this project and how, how they might congregate over time and how that might affect their later processes. So the formation of massive stars is still very debated. So it's still important to study massive stars as well, because we can also gain insight on how they drive galaxy evolution. There's two main debated theories: core accretion and competitive accretion. Core accretion is a theory that suggests that there's preformed cores of gas, just like how I mentioned there's gas cores that form from molecular clouds collapsing. And over time, they might condense or congregate into one or several massive stars. So that's one theory. Another theory is that these cluster of massive stars form when they're kind of all in one region and they're competing for materials in this gas cloud. So one star might just end up accreting or getting more of that material than other stars might. So understanding the clustering or the young formation of massive stars is important, and that's what we look at. So I mentioned galactic H2 regions earlier in the title, and just for a little background, an H2 region is basically a fancy nebula. They're created from young massive stars ionizing nearby gas clouds, and what that means is that when we have like a cloud that's primarily consists of hydrogen and it's ionized, we get H2, or a negatively charged hydrogen atom. And so this image is kind of like an idealized image of what an H2 region is. But these regions are very high in heat and density, and they're ideal stellar nurseries. So we look at these regions a lot. One really good example is the Orion Nebula. Lots of H2 regions there. They're typically or they don't last as long. So they're during their lifetime, they contribute a lot to their local stellar neighborhoods. These are the two regions that I looked at, W49A and W51A. W49A is a more distant and smaller H2 region, but it is still very luminous, so we looked at it. And W51A is a much larger and closer image as well, or H2 region. And these images that you see here are condensed images taken from different telescopes at different bands. So it's not just one image that we took, but it's several overlaid images. And a little bit about the data that we use for this project. We use SOFIA archive data from the forecast instrument. This is SOFIA. It is a now, unfortunately, dead telescope. It is decommissioned, so it does not run anymore, but thankfully we have a lot of archival data that we still have to use. So we use the forecast image to observe massive star forming regions, and we observed at 19 and 37 microns, and that's the data that we used. These are also very crowded regions that we looked at, so there's also a lot of overlapping regions, so we had to figure out a way to pinpoint sources, given that it was a possibility that certain stars are obscuring other stars. So an overview of what we did, we looked at two GH2 regions and we identified 77 and 23 sources. We used aperture photometry using the SOFIA forecast images, Herschel images, and Spitzer images at the listed wavelengths. So a lot of data was used, but it will make sense in a minute why we use so many different wavelengths for creating our SED graphs. So we built SEDs, or spectral energy distribution plots for all of our sources. And then we used a Python code called SED Creator to model them using a prior model grid developed by my advisors. And this was then used to extract stellar parameters for each source. We used a minimum spanning tree and mass segregation ratio analysis to then take those pinpointed sources and the parameters that we extracted to calculate the spatial and mass distribution. And this is the primary goal of this project. The spatial and mass distribution will tell us exactly how significant the mass and space, like if we know the mass is significantly subclustered, then it tells us a little bit about how massive stars move over time. Yeah, so we're gonna go into the first steps. First, we had to identify the sources. So we took the 37 micron images based on prior research. It was decided that the 37 micron image was perfect for pinpointing sources using the dendrogram function. And what this basically did is that it subtracted all background noise and background flux and pinpointed these sources. And this is just a preliminary source identification. We had to go through a lot more iteration afterwards to finalize our source list. And we also used a version of SED Creator developed by Zoe Telkamp. She's a postdoc at UVA, I believe, also on the VICO team. And she created this in prep for SOMA 5. And SOMA 5 is the 5th paper in the SOMA series, which is basically just SOFIA archival paper series. And my project is kind of like a branch of that. And these were our final or preliminary plotted sources. For W49A, we got 31 sources, and that's the top left image. And then at the bottom here, we have W51A with 88. Like I said, W51A is almost twice the size of W49A. So it's expected that we have more sources in this region. And then aperture photometry. This was my least favorite step. This took a really long time. The aperture photometry basically takes our inner radius or our flux radius and then the outer radius or 2 times our aperture size. And then it removes the background flux and iterates through these crowded regions to pinpoint each source and then its flux radius. For W51A, this code took an entire day, like 24 hours to run. So I just sat there and then it ran. And every time there was an error, I had to remove the null source and then run it again. So it was really fun and my favorite part of the summer. And ultimately, we got these 2 images. We used the Herschel 70 micron image as the basis because previous papers have used this band from this specific telescope to do this step. And then we got our predominant sources. We did have to also do source masking. So then it took all of these sources that we found in the aperture step and then created individual masks for each star at every single wavelength that we observed. So for all the 37 micron images, all the 19 micron images, 70 micron and everything, we created an image like this to make sure that our source was an actual source. And if it wasn't, we removed it and then ran the whole thing again. So this is probably the most tedious part, but then we ended up with 77 sources in W51A and 23 sources in W49A. So these were the first steps before we could run our SED. So now that we have our sources, we can basically build our SEDs. And what is SED Creator? A special energy distribution plot is a graph of the energy emitted by an object as a function of their different wavelengths. So earlier I said we used a lot of different bands, and that is because it's crucial for our SED building process. And it is a Python package that was developed as a part of SOMA 4. And the original one was actually created for regular regions, so not crowded regions. And the new one that Zoe Telkamp created for SOMA 5 was still experiencing a lot of issues. So this project was kind of the gateway for training the algorithm to use like data from crowded regions, if that makes sense. I wanted to pause and ask if there are any questions on like the preliminary steps, because I know I flew through that a little bit.
You talk about the source. Is that something that shows up using those specific wavelengths? If you take an image in that wavelength?
Yeah.
and you see something in that one wave, that's considered a source.
Mhm.
And those sources, those wavelengths were picked for what particular reason? Why would they suggest that there is a massive?
So, that's a good question. Yeah, so prior papers, there was 2 papers pertaining to both of these regions individually. And prior papers basically found that anything less than 19 microns didn't show all the sources. And then anything much greater, the region was too bright where we couldn't pinpoint the sources, so they kind of played around with it. And they found that 37 microns was like the best, middle ground for making sure it wasn't too faint. But then it was also not too bright where the light was obscuring, or the dust particles that are kind of, so we use infrared data or infrared telescopes. And that kind of allows us to look through any dust that's obscuring these regions. And so sometimes when the photons hit the dust particles, it might be at a certain wavelength that might be too bright, and then we can't see the actual source clearly. So they found that that was the happy medium for looking at the source.
Was there a particular signal noise ratio of the threshold or something you're shooting for? And how much did your signal have to be above background to accept it as valid?
I don't think there was a threshold. It was kind of, those papers were kind of like, I'm not actually sure. I don't really know how they did that. But I do know that that was the background literature that I did read prior to doing this project was that we pick these wavelengths, or we do aperture photometry at 70 microns because through several research projects from different groups, that was the kind of common, yes.
I think the question was more, you
Yeah.
find the larger aperture,
Oh.
what was the criteria for this as a source above the background?
Oh, okay, I understand. Yeah, so that is a good question. So we, let me go back, actually, how do I? Oh, no. Okay, I'll just explain. But it was basically, so the iterations that we did in the aperture photometry, it basically took that long because it would take 2 sources that were kind of close to each other, and whichever one had the more, had the greater background flux or the greater aperture radius was considered the more predominant source over another one. So that's how we removed sources over time, and set that as the basis. Does that answer your question?
Yeah.
Okay. Okay, yes,
Explain aperture radius again.
sure, yeah, so,
First, amateur astronomers
yeah.
can't even think of an aperture of a telescope. I don't think that's what you're talking
So aperture photometry basically so we'll take the flux, so we'll take the inner flux, or the most prominent flux radius. So flux is just the intensity of the luminosity in that surface area
about.
region.
Like the size of.
Yeah, and then there's also kind of like a fuzzy outside background flux. And so we it's hard to tell that line between the actual flux and the background flux. So we kind of take what we see as our actual flux, and then we multiply it by 2. And how we have the two times the aperture size, so that's our outer radius. And then we the algorithm will take, so for example, these 2, which are very these are overlapping, but this one has a much larger aperture radius. So it's gonna pit these 2 together and say, okay, or maybe there was another one in there too. And so we pit them together and we're saying, okay, this one has the more significant aperture radius, so we can pinpoint this as a source, and then the background of a null source that we might have detected is actually just a part of the 2 times this source, if that makes sense.
So does aperture have flux units or angular size units? That's what
I think it's angular size units.
Okay.
Yeah. So we're taking the physical size of the actual aperture, yeah. Okay, so results. So we went through that. Okay, so how to build an SED. So we basically took all 10, we had results at 10 different wavelengths. Our bottom 4 are Spitzer observations. And our middle 2 are our SOFIA observations. And our top 4 are our Herschel observations. And the way we set error bars on this is basically for wavelengths greater than 100 microns, we use the background flux that I was talking about as an error. And then for our wavelengths less than 100 microns, we use the fluctuation of the wavelengths themselves as the error. I'm not sure why. This was kind of just the standard that when we're dealing with these certain wavelengths, that's the standard that the code kind of runs. And then our data points that are shorter than 8 microns are used as upper limits. So that basically just means that 8 microns is a very small wavelength to observe these regions at. So we set that as the upper limit, and anything less than that, any fluctuations less than that are error bars. Yes.
So what is the left side, the vertical? What is that measure?
I'll get into that in just a moment. So the fitting, that's a good segue. So the way we fit the SEDs, we're gonna look at this bar on, did you say on the right side, this one right here? So we fit this curve with the model grid that I was talking about earlier. So it's a grid of the most common models or the most common star models. And then we look at the chi-squared parameter. And basically, this measures the quality of the fit. So all these colors that you're seeing indicate how good of a fit this black line is. So this black line is what comes out of the raw data. And then all of these colorful lines are lines that come from our model grid. So the quality of the fit, if our chi-squared is less than 1, it's our best fit. So the more red you are, it's the best model. So you can see this is a good example of a SED because the best models kind of coincide with the black line. So we were able to find some good fits with our raw data. And then anything that is less than 2, so the purples, blues, greens are good fits, but we don't consider them to be the most ideal fits to use in terms of constraining our stellar parameters. So from the SED, we can constrain these parameters such as our M star, so like our star mass, our core mass, surface density, luminosity, and we average these values over the good models. These are the SEDs that we got from our W49A sources. This isn't all of them, but this is some. And these are the ones from W51A. And you can see that some of them aren't good SEDs. So I want to point out specifically the one with a lot of red over there. That one is probably a source or a null source that kind of didn't get taken out during our iterative process. Because it's saying that there's all of these really good models, and but there really shouldn't be that many. So there's something that went wrong there. So we had to go back and kind of take those sorts of sources out. So I just wanted to include that one in there as an example. So I mentioned that we constrained all these parameters. And so one significant one in determining whether or not we're dealing with massive stars is plotting our surface density against our stellar mass. So the sigma clump is our surface density right here. And to kind of explain that a little bit further, our surface density is just, how many grams per cubic centimeter. So the more massive stars should have a higher surface density. And then our M star is just the mass of the star in terms of solar mass. So if you look at it here, we have a red W51A and our black W49A data. And we can see that we have a relatively high, or we have a pretty good spread of our surface density, but we have very high star mass. So we are dealing with massive stars. But if we look at I'm going to go over here. If we look at this graph right here, this is our data plotted over previous surveys done of these areas. So we have our SOHO 1 through 5, IRDC, or infrared dark cloud data, and then we also have some theoretical lines as well. So our data kind of coincides with or agrees with the previous SOMA surveys. But our what it does show, SOMA 5 and this SOMA 1 through 5 and this project, is that this red line right here is our Helmholtz theory, and that basically just was a prior theory that basically said that all of our massive stars have to have a surface density and mass past this line. But we can see that through actual like data analysis that that's not the case. And we have a lot of massive stars that have lower surface densities, but they're still classified as massive. Any questions? Yes.
What's the green one? The green dot is on? I didn't ask the same one, number one, the green dot.
I think that was also I think both of these are theoretical like lines that they plotted over from like previous papers, but it was kind of just to compare our data to those and show that they aren't necessarily correct.
Your upper mass limit looks like it's about 60 or 70 solar masses.
Yeah, I think the highest one we recorded was 55 solar masses in both regions. Let me see if there is anything else that I missed. Yeah. So this is the more important part, our analysis of the MST and MSR. So before, this is my least favorite graph, but it's important in understanding the next one. So our distribution function basically takes, it's an iterative process that takes any any pair in the cluster, and then it finds a normalized separation between those two sources spatially. And then so our P on the y-axis shows our number of pairs that are at a certain separation S. And then S is their normalized distribution. So you can see that in W51A, we have two kind of regions or two areas where there's like significant spatial subclustering of stars. So these two peaks are kind of two areas in the region where a lot of the stars are at a close separation. But here we can see we do have some close separation, but it's definitely more normalized throughout the region versus there. So this kind of tells us that before any knowledge of the mass distribution in this region, we can already see that spatially we have some sort of significant subclustering. But it only really means something to us if the mass in the subclustered regions also happens to be the most massive stars in those regions. So then we take our distribution function and then we can feed it into our minimum spanning tree. And the MST function basically connects all of our sources spatially with the shortest distance between them without creating any loops. So we get a very clear image of exactly how close each star is to its companion or its closest companion. And so we can see very clearly that, like I said earlier, that we could kind of tell earlier, there's two regions of subclustering in W51A. We don't know if it's massive, like if it's mass significant at all yet. And then in W49A, we can see that we have some subclustering, but it's definitely, like we predicted, more normalized in the region. And the Q parameter number here basically takes a ratio of these spatial region or these spatial like separations, and anything less than 0.8, basically the lower you go, or the lower your ratio, the more significant your clustering, and the higher. So 0.8 is kind of like the cutoff. You have a more normalized distribution. So W49A is kind of cutting it. It's not necessarily considered subclustered, but it is on the cusp.
Any particular reason why you chose minimum spanning tree versus other clustering techniques? Just general hierarchical clustering or something like that, or that was just convenient to do that? It looks like it's just a means to an end, but you know?
That was just, what, I was a first year when I did this project, so that was just what my advisors, suggested based off of like prior papers. I didn't really know of any other,
So there's, you don't interpret the, you know, these longer arc lengths as having significance, in other words, you know, between between your two circles on the
Yeah.
left or whatever, that big arc that kind of separates them isn't
Yeah.
particularly interesting then, I guess.
It is, there's still a lot of work to be done on this project, so we're still looking at, so what the primary or like the first leg of this project was to just see what the mass segregation is, so just to get our numbers and get our, see how the distribution is. We have a lot more analysis to do, as a group to see what it means, but that's a good question to keep in mind. Okay, and then our mass segregation ratio, this was the ultimate goal of this project. So our mass segregation ratio, we use the M-STAR data from our SED building process combined with the MST analysis to derive our MSR ratio. And so what this basically means is that we take the length of the N sources or of N sources randomly selected from the cluster, and then we take a ratio with the length between the most massive N sources in the cluster. And then what this basically gives us is, so it will give us a ratio, so the lambda MSR, and the higher the ratio, the more significant the mass subclustering. So we can see that in W51A, we have a higher lambda MSR in the 20 most massive sources. And then we can see in W49A, we have a high ratio for maybe 2 of the sources and like some of the ones down here, but nothing as dense as W51A. So this basically allows us to conclude that in W51A, we have significant subclustering spatially, but also with mass. So all of our most massive stars also happen to be very close to each other. And and the reason why this is important is because earlier we were talking about debated theories surrounding massive star formation or supermassive star formation. And if these are young stars that are already congregating, because these are H2 regions consist of mostly young stars that are kind of already spatially very close, it can maybe allow us to support a core accretion theory where these cores are kind of like accreting and moving towards each other to maybe become one or several massive stars one day. And so one thing that our group did, just to kind of put this into perspective, is we kind of looked at our actual data in comparison with some previous data. We looked at the Moser 2020 papers. This was done on an IRDC, so an infrared dark cloud region, very early, very, very young region. And this is just to put our data into perspective. So what this basically is, we have our high and low, maximum and minimum theoretical maximum, or what is this? The extreme theoretical minimums and maximums, and then the red is our actual data that they collected. And we can see that it kind of looks similar to our W49A region where there isn't really a lot of subclustering. So what this could suggest is that, you know, it could mean that over time, as a system ages more, it will start to look like our W51A graph, or it might not. And so that's something our group is looking at right now. We're looking at the evolution from data from IRDCs to H2 regions to see, you know, is it going to stay like this, or is it going to move into something like that where our massive stars in the region congregate together over time. And then this one, yeah, so this one does have some subclustering. I forgot I included that in there. It has a Q parameter of 0.6. So there is some we could predict that there is a little bit, but there's definitely more to look at on that realm. And yeah, to summarize, we looked at GH2 regions, W51A, W49A, and we found 77 and 23 sources. We completed our source aperture photometry using a special version of SED Creator, and we also helped develop SED Creator to work with crowded regions. And then we also built our SEDs to extract our stellar parameters and performed MST and MSR with these parameters to find our smooth distribution in W49A and our clumpier distribution in W51A, with approximately 20 of the most massive stars having notable mass segregation. So next steps and things to fix. Some of these sources have large errors in the SED fitting process. So like I was showing you earlier, some of our graphs are not ideal. The fitting process makes it, and so that makes it harder to constrain more accurate parameters for our MST and MSR analysis. So this just is fixed by doing multiple runs of the same code over and over again. And so by doing that, we can improve our source list. We can cross-check our source list by maybe taking in different wavelengths into account. And then once we do that, we'll hopefully be able to finalize our results and then move on to publishing. Fingers crossed. But yeah, any questions?
Yes.
Yes.
So you mentioned earlier, you said that I think the water star you said was kind of flat solar. Is there any assumption that maybe other stars are too close, and that's why that was so big? Is that the,
Yeah, I mean, it could be that that massive star is a result of prior massive stars colliding. I didn't include this in the slide, but it would help to do a chemical analysis or like look at more of the composition of the stars in these regions to see if there is any evidence of like a late stage massive star. But we have not done that yet. So
When we know if some of these massive stars are actually not atomized through binaries?
it could be that, I mean, it could be a binary, but again, this code is meant to work with these crowded regions, so probably would have, these are binary, like a lot of these are binaries, like all together, like if you look at some of our images here, so actually here you can see that this top one right here is two massive stars that are at a close separation. That's a binary right there. A lot of our W51A data binaries, or they're just like stellar neighborhoods that are very closely bound. So yeah. Yes.
Is there any study to see if the stars are kind of moving toward each other or if there is any movement?
Yeah, they move slow. So it's kind of like not in our lifetime. We can't really like see how it moves. Like in 10 years, it's not going to be a significant amount of movement, but we can compare it to similar stellar neighborhoods using like a chemical analysis. So we can compare it to a region that's very similar or a younger region. But I'm sure there are ways to see, or other research projects to see.
What's the oldest data you have for those two regions?
The oldest, sorry.
Data? So I can
We have quite a bit. There was the prior papers that I read before this were written in 2019 and 2020. And they were also using SOFIA archival data, but I think there might be some older, I don't know if any other older telescopes looked at it at the same bands or with the same intent, but there might be other archival data. Like we did use Herschel and Spitzer images, just because we didn't want to just use the SOFIA images. We wanted to compare it with, compare and use data from other telescopes to ensure that we weren't eliminating any possibilities of a source observed from another telescope. Yes. Hopefully. We'll see. By the end of the year, next year. Yeah.
Were there other regions of interest that you looked at, and how many others were there potentially?
We didn't look at any other regions. These were kind of the two regions that I was given when starting my project. So everyone in the VICO program is, they have different projects, but everyone gets different regions to look at for different reasons. So I think our I think our group was given data from these specific regions from the SOFIA archival project or, but I would be interested in looking at other regions to see if there's subclustering or anything like that. I think it's that this type of analysis can be done on a lot of regions, and then you can compare and see if our results are significant or if it's just like once in a random thing that happened.
Yeah, I was thinking if there were enough regions, you could use AI to
Mhm.
kind of determine which ones are candidates for clustering and
Yeah.
how they interact with each other.
Yeah, definitely.
Big, larger scale.
Mhm. Any other questions?
That actually prompted mine. I guess it's quick. You asked most of what I wanted to know about, but these Sophia, Herschel, all these other things, I know of them, but I don't know all the specifics. Did they do surveys?
Yeah.
Or, you mentioned that you picked these particular regions. And, you answered the question before, but I'm just curious, it's like, how much overlap is there of those various telescopes? Pick regions, or you're just given, these are the only places that have overlap.
I think so we had the SOFIA archival data. And so we had those regions, and I think what our group did prior to me joining was that they looked at, what other telescopes or what other studies have been done and what data did they use, and they use that as well. So they kind of
you
integrate.
found the ones that intersected, that had data from both telescopes.
Yeah.
For all telescopes,
Mhm.
and they kind of look at that and see what's going on.
Yeah. Mhm. And I mean, there's obviously like more data now. If I wanted to submit like a request for JWST, that would be awesome. It's like, or do they want to observe W49A and W51A? That's up to them.
How far down is it observed in the bands with?
Um,
I thought those were at the short end of the spectrum.
not all of them. We have some higher, the Herschel ones, I believe, are higher wave.
Yeah, those were some.
Those were like, the base was 70, but it went up to 500, so.
No further questions.
I got a question.
Yes.
I have a question.
Like,
Kevin has a question.
Yeah.
So mine's really basic though. So you started this in the first year, your first year.
Yeah.
In high school, what did you know about any of this stuff?
I did do research in high school about stellar evolution around black holes for my senior project.
Okay.
But this was I did this the summer after my first year. And it was a good introductory or introduction into collegiate research. It's a lot different. But I was able to kind of learn the necessary repertoire like my first year in terms of coding and astronomy basics. And then I was able to go into, I also did research my first semester with a professor as well. So that was also, it set me up to use like data systems and like learn how to use research interfaces.
And you were doing that while you were in high school or preparatory to?
Yeah, but I did it, I've been doing research since I was 16 or 17. So it's been a while since I've been kind of like I've been working with data and learning astronomy basics, so.
And were you considered like brilliant doing this at the time? The level of.
You didn't start out with astronomy 101, but you started out.
I started, yeah, I mean, when I got to UVA, I started with just the intro to astronomy. It wasn't even like an astronomy majors course. They just pre-enrolled me in like the stars, galaxies, and universe. That was like my first official astronomy course. When I was in high school, I just did like research on my own to learn. But I wasn't like formally given like any classes or anything until I got here. Yeah.
These two regions, is it something that's old enough to allow a high mass stars to run this life and leave a lot of neutron star or other aspect holes?
No, so these are younger regions. So that's why we're looking at early stage mass segregation. H2 regions typically have a shorter lifespan. And by shorter, I mean like short enough where we don't really look at them for late stage evolution. But the research that I am doing now, I just started a new project, is more about stellar death, planetary nebula, and how supernovas, or red giants and supernovas have like, or it's more on, but I won't get into. But yeah,
It gets more questions. How old in terms of years would a young system be, a young H2 cloud with some solar?
that is a good question.
About a million, 10,000?
I think that I remember that I like the numbers on the tip of my tongue. It's like it's young, it's old, but it's young relatively compared to
So a million.
a regular. Yeah, it's more like something 100 million or something million, which is young. Yeah.
Right, exactly. You know, I cannot be adequate recompense for your wonderful talk. This is just a tradition. Every speaker that presents us with a talk gets from us an internationally coveted cast mug. Now I want to attract your attention to the back here. It shows you major meteor showers, dates, and what the name is.
Oh, nice.
And so, as you drink your coffee, you can check the date.
You remind me. Thank you.
See if it's something outside. Yeah, the meteor was so.